Okay, let's unpack this. When you think about cities, we've constructed these massive monuments of steel, glass, and concrete.
Structures that were designed to be rigid, heavy, and, seemingly eternal. But the source material we've gathered today, which is all operating under this fascinating banner of mycopunk, it proposes a truly radical alternative,
Which is?
transforming these rigid structures into living, adaptive organisms,
Yeah.
ones that actively participate in planetary health.
And we're not just talking about adding a few green roofs here.
No, no, this isn't just about painting a building green. This is a full-scale change to the very operating system of the built environment.
So our mission today is to really dive deep into this vision, this lightweight revolution. And we're going to do that by examining the two interconnected concepts that seem to hold it all up. First, mycomaterials.
The building blocks themselves, grown from waste.
And second, these things called exostructures, these adaptive architectural skins that you can wrap around our existing heavy infrastructure.
And we're going to look specifically at how these systems manage to translate these deep ecological principles, what the sources call mycelial logic, into practical, functional, and frankly, necessary solutions.
Solutions for what exactly?
Well, for everything from mitigating the urban heat island effect and managing floods to, enhancing human quality of life and completely redefining our relationship with the more than human world. All the life in the city.
What I find so compelling right from the start is that this revolution begins with a kind of conceptual retreat.
What do you mean by that?
Well, we're consciously moving away from what they call heavy architecture. The concrete monument built to last forever.
And moving toward what?
Toward tent thinking. It's an architectural philosophy that's all about lightness, adaptation, and temporality, but it's achieved with modern layered technology.
So the exostructure is, in effect, a return to architecture as a membrane again, instead of a monument.
Exactly.
That historical reference to things like tents or yurts is so crucial here. I mean, historically, structures you could carry, assemble, and disassemble gave human communities resilience, mobility.
But we traded that for permanence.
We did. We gained solidity, but we introduced rigidity. And paradoxically, that created a kind of long-term fragility.
Right.
The mycopunk insight is that you don't actually have to demolish that permanent structure, that concrete cave we all live in, to get adaptability back. You wrap it. You wrap it in something designed to breathe and grow and change, and that creates this functional, productive gradient between the inside and the outside.
Which is a huge difference from conventional architecture.
Oh, a world of difference. Conventional architecture insists on a hard binary boundary. This is all about blurring that line.
And that focus on the gradient, it forces architecture to acknowledge its own limits, its own temporality, which is just a massive paradigm shift.
Absolutely. When you design a building explicitly for continuous modification so you can unbolt it, disassemble it, reuse its components.
It stops being a fixed, sunk cost.
Exactly. It transforms into a liquid asset, an inventory. I mean, you have to wonder about the friction there, right? Doesn't that completely upend our established notions of property value and depreciation?
It has to.
It absolutely challenges the financial status quo. I mean, think about it. We currently rely on materials that last for centuries, yet we arson demolish buildings after just 50 or 80 years.
Because they become functionally obsolete.
Right. And they generate these mountains of toxic rubble. The waste is financial, it's ecological, and it's cultural.
So by designing for disassembly from the start, mycopunk embraces what the sources call temporality as honesty.
That's a great phrase. It's acknowledging the structure has a lifespan, whether that's 30 years or 100. But when that time is up, the components don't become environmental waste.
They become the valuable substrate for the next generation of building.
That cyclical material logic is, I think, the absolute prerequisite for this entire movement.
Okay, so let's move from the philosophy of change to the actual building block that makes it all possible. The entire revolution really hinges on this core material science, mycomaterial.
The mycomaterial is a genuinely groundbreaking component. It really is.
So what is it fundamentally?
It is lightweight, it offers superior insulation properties, and most importantly, it's fully compostable at the end of its life cycle.
And where does it come from?
That's the key. Its origin is what makes it so unique. It's derived entirely from waste streams, specifically industrial and agricultural waste.
So we're talking about things like...
We're talking about shredded cotton fibers, hemp, straw, sawdust, and this is a particularly vital one, textile waste.
Wait, hold on. So the solution to fast fashion's immense overproduction and waste crisis is to literally turn our cheap, discarded clothes into durable, high-performance architecture.
That's it. It's a profoundly closed-loop system.
That's incredible.
It's closing a massive, costly, and incredibly polluting loop. I mean, the current linear economy, it either discards these materials or it burns them. The mycomaterial industry consumes materials that the system has literally nowhere else to put. It just turns them into value.
And beyond the source material, what are the properties? How
Yeah.
does it stack up against, say, concrete or drywall?
Well, it offers resilience that actually rivals conventional components. It is naturally fire retardant. It's VOC-free.
Meaning no off-gassing of volatile organic compounds.
Zero off-gassing into our living spaces, which is huge. And it offers superior sound absorption compared to drywall or concrete blocks.
I noticed the sources really highlight its customizability. They say it can range from a soft sponge-like insulating panel all the way to a material with wood-like stiffness and rigidity. That seems like a massive jump in structural capability.
It is, and that variability is entirely a function of the production methodology. It's sophisticated, yet it's decentralized, and that system is called the Mycofactory.
The Mycofactory.
They recognize that traditional centralized cement plants are, frankly, logistical nightmares. So instead, the Mycofactory is designed as a modular living organism.
And what does that mean in practice? Modular.
Each module is built to the exact dimensions of a standard shipping container.
Ah, okay. So containerization is key here.
Precisely. It makes the entire production system stackable, mobile, and easily transported by the global logistics networks we already have. Trucks, trains, ships.
And that decentralization allows the factory to move closer to the waste source.
Yes, exactly. Maybe it's next to a massive textile recycling hub or closer to the construction site itself. It dramatically cuts down on the transport emissions that are just inherent in the heavy construction industry.
That alone addresses a huge chunk of the construction industry's carbon footprint. So let's walk through the production line inside one of these factories because it's this fascinating blend of biology and industry.
It really is. It's a four-stage process, and it all starts in the mycology lab module.
Correct.
This is the sterile, nutrient-rich environment where they cultivate specialized fungal strains. They often use liquid culture in these sophisticated bioreactors. This is where the biological intelligence that does all the growing is nurtured and, amplified.
So that's the starter culture. Then you need the raw material to feed it.
Yes, that's the substrate processing module. Here, the raw biomass, the shredded waste materials, is measured, it's mixed with nutrients, and it's meticulously packed into reusable steel molds.
And those molds define the final shape.
Exactly, whether it's a standard construction block, an intricate panel, or even a structural beam.
Okay, the next stage sounds crucial for quality control.
The sterilization module is perhaps the most important technical step. The filled molds are moved into a high-pressure steam chamber.
Why is that so important?
Because raw waste material is just teeming with competing bacteria, mold, other spores. If you don't achieve perfect sterility, the mycelial strain you want will be outcompeted, and the product will either fail or become contaminated.
In the final step.
Correct. The inoculation and cultivation module. The sterile molds are cooled down, and then they're injected with the liquid culture from the lab.
And then you just wait.
You wait. Over a period of several days, and the actual growth period can vary based on the strain and the product density, the fungal threads, the mycelium, colonize the entire substrate. They naturally bind all those shredded fibers together into a coherent, solid block.
That sponge-like material still needs to achieve architectural durability and strength,
Right.
especially for structural components.
That's where post-processing comes in. You have to adapt the material for different demands. For, say, interior insulation, just simple drying is often enough.
But for structural use,
For structural use, the block undergoes intense hydraulic compression. This process uses massive pressure to increase the material's density. It forces out any remaining moisture, and it aligns the internal mycelial matrix.
and that alignment is what gives it its strength.
It dramatically boosts its hardness, strength, and load-bearing capacity. It essentially transforms it from a soft growth into a durable, solid block.
And for anything that has to face the elements, rain, snow, direct sun, the exterior applications, you need some serious weathering protection for that.
That requires the advanced resilience layer, silicate reinforcement. And this isn't just a coating, it's a deep chemical process.
How does that work?
The mycelium component is put in a vacuum, and it's impregnated with a solution containing sodium, potassium, or lithium silicates. As those silicates cure, they coat the internal fungal structure, and they polymerize. They form this mineral satin glass-like outer layer. Silicate reinforcement chemically merges with the material itself.
So it's part of the block, not on top of it.
Exactly. It creates a highly durable, water-resistant layer that is also extremely weatherproof and resilient against mechanical damage.
So you end up with this high-performance material that is structurally sound, derived from waste.
It's an engineered biological composite designed for decades of performance. It scales not through massive corporate centralization, but through the logic of ecology, the mycofactory. The system literally converts linear urban waste streams into circular value streams.
And in doing so, it creates localized, sustainable, high-skill jobs.
In areas that might have been economically marginalized, it reframes economics to function like ecology, regenerative, local, and collaborative.
That transition is profound. So we've established the material, and that brings us to the second core concept, the exostructure, the scaffolding system that wraps conventional buildings and transforms their function.
The exostructure is the architectural intervention that makes this whole conceptual shift tangible, and it's important to stress that it is defined as a productive exoskeleton. It's a modular, adaptable, load-bearing layer that acts as a living skin for the existing conventional building that it surrounds.
So to really understand the exostructure, we have to challenge the most fundamental element of heavy architecture, which is the wall.
The sources get quite philosophical about this. They really do. They describe the wall as the original wound in our relationship with the environment.
The original wound.
The absolute rigid binary that separates inside from outside, human space from nature. And while it provided security at scale, the proliferation of these rigid walls has created massive ecological problems.
The urban heat islands.
Urban heat islands, excessive stormwater runoff, and this sense of profound social and psychological isolation for the people living inside.
So the exostructure steps in not to destroy the wall, but to mediate it.
Precisely. It doesn't replace the wall, it adds a gradient. It creates an occupied, accessible, liminal space, or what they call a feral edge, between the building's interior and the hostile street environment.
And this transitional zone becomes a space for what?
For social experimentation, for localized food production, and critically for collaborative life that's shared between the human residents and the living biological systems that are integrated into the structure.
And that ability to mediate the climate, that's the immediate measurable payoff.
Absolutely.
Our sources point specifically to retrofitting existing, often poorly insulated urban housing. Think of those concrete residential blocks from the mid-20th century you see in a lot of European and North American cities. They're thermal nightmares.
And this is where the physics of the exostructure prove their value instantly. The external scaffolding, coupled with the integrated moss walls and vegetative panels, acts as a massive passive system.
How so?
It interrupts direct solar radiation. It effectively shades the original heavy wall. This intervention dramatically reduces thermal gain, the heat absorbed by the building, by a documented 10 to 20 degrees Celsius on peak summer days.
That's not marginal savings.
It translates directly into public health and energy resilience. This system creates what they call a thermal blanket that breathes. The moisture released by the plants further cools the microclimate through evaporative cooling. The resulting effect leads to substantial, measurable energy savings. We're seeing in early pilot projects 30% to 40% reductions in heating because the insulation traps heat in winter and cooling costs because the shade prevents heat in summer.
And beyond temperature, it transforms the entire sensory environment of the city, the sound.
Think about noise pollution. The rigid materials of the heavy city concrete, glass, they reflect sound waves, amplifying ambient urban noise.
Right.
The moss wall panels and the vegetation integrated into the exostructure act as giant, porous sound absorbers. They dramatically drop ambient noise levels by 10 to 15 decibels. It moves the street from a state of chronic stress to one of relative calm. Mycopunk architecture asserts change and relation.
Okay.
The design is explicitly for continuous modification. It allows the human community to keep retuning itself as needs change. The very design principle being bolted together, modular, legible, it invites ongoing adaptation.
Which they term architectural democracy.
Exactly. You aren't beholden to the original designer's vision from 50 years ago.
But practically speaking, if the components are meant to be unbolted and reused, How does that translate into a long-term investment strategy? That seems like a challenge.
It fundamentally resists the whole notion of architecture as a fixed asset that's just destined for a landfill. By embodying this logic of temporality as honesty, the exostructure acknowledges that infrastructure has a life cycle.
It's not pretending to be eternal.
Not at all. And when the structure is legible, when you can see how it was put together and what state the components are in, that structure is the information.
While legible, exostructural systems allow for early repair, modification.
And efficient resource routing. They are resilient because they are constantly being maintained and adapted, not because they were over-engineered for some static future that was never going to arrive anyway.
So the exostructure isn't just a physical layer. It's a dynamic framework for a more democratic and resilient urban existence. We're moving into section 3, the new urban metabolism.
Right, and this is where the systems integration gets really complex and fascinating. It fundamentally changes the flow of resources within the building cluster. We should start with the most essential element, water, the integrated hydrological cycle. The city becomes this hard, impermeable surface that just shunts water into overburdened sewers, and that leads to urban flooding. The exostructure reverses this completely.
Oh.
Its newly created horizontal surfaces, like the walkways and platforms, are designed for catchment and cycling. They capture rainwater, they slow its descent, and they route it immediately into localized storage tanks.
Which are integrated into the structure itself.
Right, beneath the structure or within the scaffolding columns.
And that stored water then becomes the input for all the biological components.
Yes. It fuels the entire vertical garden system, the moss panels, the hydroponics. This localized cycle means the plants and fungi are constantly using that stored water. And critically, through transpiration, they release that moisture back into the local microclimate.
So they're completing a miniature localized watershed. It's not just about using the water, it's conditioning the air. And the cumulative effect of that at a neighborhood scale must just greatly reduce the stress on our often ancient city infrastructure.
Massively so. By preventing that fast runoff and reducing the volume of water entering the municipal sewer system, this structure mitigates the risk of flooding during heavy rain events, which is, a climate adaptation necessity now.
So the structure acts as a giant intelligent sponge.
That's the perfect word for it. It slows the water down, it processes it through biological filtration, and then it releases it gradually. This mediation of the flow rate is just as important as the quantity of water it manages. It provides resilience against these destabilized weather patterns we're all experiencing.
Okay, so water management ties directly into local food production, which uses that new horizontal and vertical space created by the scaffold. I want to hear more about these high-efficiency aquatic scaffold systems.
This brings us to what the sources call the duckweed protocols. And this is not, a couple of tomato plants on a balcony. This is not subsistence farming.
This is high-efficiency, resource-conscious food and nutrient generation.
Precisely. Specialized aquatic scaffolds, aquaponic or hydroponic tanks, are integrated into the building platforms to cultivate these fast-growing crops like duckweed.
Why duckweed?
Duckweed is extraordinary. It's the fastest-growing vascular plant known to science, which makes it intensely efficient at converting sunlight and nutrients into biomass. They can optimize the output for specific high-value compounds. For example, production of plant-based omega-3 fatty acids. Others are about optimizing protein accumulation to create a complete sustainable food source that can be harvested and processed right there.
And of course, this local food production generates waste, which brings us to the true circular nutrient economy.
Food scraps, plant cuttings, residual biomass from the duckweed harvests is fed directly into integrated bioreactors.
Bioreactors, where do you put those?
They're often placed strategically, maybe integrated into northern-facing facades where they can maintain stable, moderate temperatures year-round, which is ideal for microbial activity.
So the bacteria are essentially acting as the city's digestive system.
That's a great way to put it. These anaerobic digesters break down the organic material. The output is twofold. First, you get captured methane, which is cleaned and used as biogas for local cooking or electricity generation within the cluster.
And the second output?
Equally important, you get high-quality, pathogen-free fertilizer. This nutrient-rich digestate goes directly back into the vertical gardens and the hydroponic systems.
Closing the nutrient loop entirely within that 200 to 400 person cluster.
They become entirely self-contained metabolic units.
Now, all these systems, the pumps, the sensors, the LED grow lights, the bioreactor agitators, they all need constant low-cost power.
Which is why the infrastructure is built around the 12-volt rewiring and distributed intelligence concept.
Okay, what does that mean?
All the integrated exostructure systems run on a completely separate 12-volt DC electrical system.
Why 12-volt DC specifically?
There are a few key advantages. First is safety. 12V is inherently low voltage and safe, which allows residents to perform maintenance or simple upgrades themselves. That's crucial for that architectural democracy we talked about.
I see.
The power is generated locally, usually by solar panels that are integrated seamlessly into the scaffolding structure. It's stored in distributed battery packs, and it's used directly by the low-voltage components, which minimizes conversion losses.
So it's like a parallel, independent, resilient nervous system for the living building.
And that nervous system needs an intelligence layer, which is handled by cluster AIs.
Now, AI can be a scary word.
Right. But these are explicitly local, decentralized AIs. They operate only within their cluster's boundaries, and they're designed to be transparent and auditable by the residents.
And what do they actually do with the data they collect?
They monitor the continuous stream of sensor data, everything from water reservoir levels and biogas pressure to energy production and the optimal growth conditions for specific crops.
And then they act on it.
They handle the complex, real-time optimization and coordination of all the routine management. They'll adjust irrigation schedules based on local rainfall, modulate LED light spectrums to maximize that omega-3 yield, and automatically divert excess solar power.
But they don't operate in a vacuum.
No, they communicate via mesh networks with AIs in neighboring clusters. They signal needs and surpluses. One cluster might signal, hey, we have excess water today, while another signals, we need a temporary power boost for our bioreactors.
So this is not some centralized Big Brother AI managing the whole city.
Absolutely not. It is a true distributed intelligence operating at city scale. The coordination and resource transfer are emergent properties of these localized, rules-based systems interacting.
And that frees up human residents from the complex minute-to-minute management.
Exactly. So they can focus on community governance and the higher-level social decisions that technology can't solve for you.
If we connect this to the bigger picture, this level of systems change demands more than just new materials and wiring. It needs a radically new social structure, a new organizational philosophy. So let's dive into Section 4, the mycelial network topology, governance, and labor.
This section is really about exploring the deep computational and biological principles that guide the social and structural design. It's what they call mycomimetic logic and emergence.
So the architecture isn't just inspired by fungi. It tries to emulate their functional strategies.
That's the core idea.
We talked about the fungi providing the structural scaffold in the material, but how does that extend to the overall structure of the city?
It mimics the fungus's deep evolutionary role as a bridge builder. I mean, think about the transition of life from aquatic to terrestrial environments 450 million years ago.
Okay.
Early plants couldn't just colonize land on their own. They needed fungal partnerships, essentially lichens, which provided the structural scaffold that held moisture and extracted nutrients from rock.
So the exostructure is performing the same function for the contemporary city.
It's providing a structure that allows human communities and ecological systems to survive and flourish in a harsh, vertical, man-made environment they couldn't otherwise inhabit sustainably.
And that structural analogy, it translates into highly efficient network design. This is the topology as information principle.
This is where the computational efficiency comes in. So the lesson applied to architecture is that legible exostructural architecture is functionally superior because the structure is visible, it's bolted, exposed, layered. The structure is the information.
And that transparency facilitates immediate, efficient resource routing, repair, adaptation.
Because you don't waste time in energy mapping a hidden system. It's all right there.
So design transparency is a prerequisite for systemic resilience and efficiency. But when you try to scale this up to the city level, how do you prevent all those local adaptations from just becoming chaotic?
You scale not by replication, but by pattern propagation.
That's the difference.
The designers recognize that copying a specific facade designed for the humidity of Lagos and just pasting it onto the climate of Lisbon is an ecological and functional failure.
Right, it makes no sense.
So scaling involves sharing the universal principles, legibility, cyclicality, multi-species design, resource optimization, while allowing the implementation to remain intensely local and adapted to the specific climate, the available waste streams, and the cultural context of that community.
The pattern is shared, the specific form is generated locally.
You've got it.
And that concept of local generation relies on organizing the human community at the correct scale, Which brings us to cellular urbanism and governance. What is the optimal social unit for this new system?
The organizational unit is the social cluster, and it's typically defined by the structure itself, say 200 to 400 residents living in one wrapped building or a connected block.
And that scale is intentional.
It's small enough to foster stable social relationships, visual familiarity, and accountability, but it's large enough to support the shared economic and metabolic infrastructure. The exostructure creates this immediate visual coherence and identity.
So residents might identify strongly with the duckweed harvesting block or the green moss-covered platform,
Exactly.
and the physical platforms and the skyways, they become the engine for social cohesion.
They become the relational infrastructure. Shared spaces require shared responsibility and constant negotiation, which is what facilitates community formation. And because the architecture is designed for continuous iterative
And
modification.
enables that architectural democracy again.
Right. Decisions about the use of shared biogas, the allocation of water for the vertical gardens, or the timing of a facade harvest, they're all made collectively.
But how are these highly complex, resource-intensive decisions managed without falling into just endless political deadlock? That seems like a real risk.
They rely on structured governance systems, most often decentralized autonomous organizations, or DAOs. The DAO model is the natural fit because these complex community decisions about resource allocation, where to route power, when to switch irrigation, they require transparent, rules-based systems that are resistant to being easily hijacked by a single self-interested party.
So they use these systems to capture consensus decision-making.
For things like maintenance schedules and resource flows, yes, it essentially automates the low-level management based on agreed-upon community principles. The system runs on rules, which frees up the humans to focus on the principles that define those rules.
That transition from individual isolation to cooperation, though, it must require an entirely new workforce.
Right.
This is the new labor of living systems.
We see the emergence of this post-industrial workforce that is focused entirely on care for the metabolic infrastructure.
And these new occupations require what the sources call symbiotic skills.
Meaning the workers must blur traditional disciplinary boundaries. Okay, a bioreactor technician, for instance, can't just be a mechanic. They have to understand the chemistry of anaerobic digestion, the mechanical maintenance of the pumps, and the photosynthetic cycles of the feedstock that's going in.
Wow.
Or a mycelium engineer. They're blending construction, material science, and gardening. Their daily task might involve applying silicate reinforcement to new panels, while at the same time monitoring the fungal health of the facade using spectral analysis,
And then there's the essential soft infrastructure labor, the human side.
which is crucial. The transition from isolated living to cooperative living is not automatic, so the roles of community formation facilitators and consensus specialists are absolutely vital.
And these are the people hired to.
Mediate disputes, teach collaborative decision-making within the DAOs, and help neighbors transition from thinking solely about their own individual apartment to thinking about the cluster as a collective subject.
So the fundamental economic shift here is that work itself becomes a form of care. Care for the living systems that sustain the community.
The labor is regenerative, it's local, and it's tangible. It integrates labor time with daily life, and it operates within these hybrid economies that combine traditional market participation for high-value goods like those specialized omega-3s with commons-based resource sharing for basic needs like biogas and structural maintenance.
The city's inhabitants are constantly tending to, adapting, and monitoring the systems they rely on.
Yes.
And this ongoing relational engagement leads to the deepest cultural change of all, the animate worldview.
If you are constantly interacting with the structure, managing the moss walls, harvesting the duckweed, tending the bioreactors, you begin to perceive the structure not as an inert, dead object.
But as a responsive, breathing, sensitive system.
Exactly. This constant relationship naturally leads to you perceiving the structure, and by extension, the broader world, animistically, as a collective subject, not just a resource to be extracted.
It's an experiential path to a relational ontology. You don't need to read the philosophy, you just need to manage the plumbing.
That's a perfect way to put it. And this perception shift culminates in the realization that the building is a collective subject.
A community.
A community composed of the structure, the plants, the fungi, the beneficial insects that are attracted to the facade, and of course, the humans.
And this demands a radical shift in design principles.
Completely. Architecture ceases to be about building for humans in isolation, and it becomes about building for a multi-species community where the health, social, and ecological of the entire community becomes the ultimate metric of the project's success.
So what does this all mean? We've covered everything from compostable materials and decentralized production to cluster AIs and an animistic understanding of urban life. The Mycobunk framework seems to be a complete, wholesale reinvention of the city's relationship with the planet.
It simplifies down into three core interlocking revolutions. First, you have the material shift. You're moving from mined, finite, and environmentally costly materials to grown, circular, and regenerative materials derived from waste, the mycelium composites.
Okay, that's one.
Second, the structural shift. Moving architecture away from its role as an impermeable barrier and a permanent monument to becoming a porous, adaptive membrane and scaffold. That's the exostructure.
And finally, the third one, the big one.
The cultural shift.
Mhm.
Abandoning the cosmology of linear extraction, of isolation, and of false permanence for one of cyclicality, mutualism, ongoing care, and the explicit recognition of the built environment as a living, dynamic ecosystem.
And it's crucial to state this is not just abstract theory.
Not at all. It is practical experimentation. There are pilot projects actively running in places like Vienna and Medellin, demonstrating that transforming cities into systems that are legible, porous, and regenerative is technically feasible.
The vision is aiming for nothing less than a planetary-scale transformation of human habitation.
And turning cities from being the single greatest source of our environmental problems into powerful ecological solutions.